We've looked at simple averages, and we know that they are kind of closely related to the boxcar filter, which is a moving average. Let's take a look at applying the boxcar filter function. First, I'm going to compute simple averages of the data. Then I'm going to compute a boxcar filter. The averages I just computed are 1-year averages. The times are evenly spaced, which is kind of important for the boxcar filter. Well, a 1-year time slice has 12 data points in it if they're monthly data like these are. So I'm going to apply a 12-point boxcar filter and have it produce a nice plot for me. Well, we can see that the data are the gray line. The thick red line is the smoothed estimates, the boxcar filter values. The red dashed lines above and below it mark out the 95% confidence interval. We can see that it wiggles around quite a bit, which is no surprise. We had noise going in, we're going to get noise coming out. But it wiggles around the true value. I can plot that again, and I can put the time on the axis. The previous plot didn't have the time values because you don't tell the boxcar filter what the time values are, so it just plotted 0 to 1200 because there are 1200 monthly values. Now I've made a plot where I put time on the x-axis because the time, it's monthly values for 100 years, so the time goes from 0 to 100. Now I can plot just the smoothed values themselves and their confidence range and compare that to the true signal. We can see that there are definitely points in time where the confidence range does not include the true signal value, but that's really no surprise. We expect that to happen with a 95% confidence range. There's a 5% chance of being outside the confidence range for each moment of time. So with a lot of moments of time, we could expect to see several, maybe even many, times when the confidence interval does not include the true signal. I can also plot the simple averages that I got before. The simple average will be exactly equal to the boxcar filter value at the time which is applicable to the simple average and the boxcar filter. Now we don't have to use 1-year time scale, we can use a 10-year time scale. There are simple averages. Let's compute the boxcar filter. Now we see that we're getting a much more smooth, it's not so jiggly. It's still wiggling around, of course, because, let's face it, noise in, noise out. But now we can see that we're actually getting something that's much more friendly. And if we compare that to this solid black line, which is the true signal, we'll see that most of the confidence intervals include the true value. There are a few that don't, but most of them do. We can also, once again, plot just the smoothed values and their confidence interval in comparison to the true signal. We can see once again that the smoothed values wiggle around a lot, but they wiggle around the true value, and most of the time, not all the time, but most of the time, the confidence interval includes the true value. We can also plot the averages we got from just simple averaging. And we can see that they really are exactly identical to the boxcar filter values at those moments of time. The confidence intervals are not exactly the same here, for instance, because for the boxcar filter, it just adds and subtracts 2 standard errors. But for the TIMAV program, it computes the standard errors separately for each slice of time, and it applies the t-distribution instead of the normal distribution. Well, the boxcar filter isn't the only filter we had. Let's compute a tent filter. Well, now we get a very similar curve, only it's quite a bit smoother. It still wiggles around, and it wiggles around about the same total amount, but it's not really jerky a lot. It's smoother on a short time scale. Let me go ahead and plot the values as a function of time, not as a function of data index number. And let me plot the confidence intervals and the true values. Now the boxcar filter followed this same line very well, but it jiggled around a lot on short time scales. This is much more smooth on short time scales. That's one of the differences between the tent filter and the boxcar filter. Also, If I plot the average values from just simple averaging over slices of time, I can see that it is not exactly equal to the tent filter because the tent filter is not a simple average. It's a weighted average with non-trivial weights, particularly here at the end. The simple average over the last 10-year time slice was down there, but the tent filter value is up higher. There, by the way, is the boxcar filter. I've plotted that in purple. Notice that the boxcar filter is following the same general line as the others. This serves to illustrate that when you apply smoothing methods, any good smoothing method will give pretty close to the same result because that's what the actual smooth value is. But they'll all wiggle around. They'll generally wiggle around in a similar fashion because they'll be averages of the same noise. Do notice that the boxcar filter in purple is a lot choppier than the tent filter in red. Well, the tent filter, the boxcar filter, they're not the only ones we can apply. We can apply a Gaussian smooth. For a Gaussian smooth, we can extend our smooth all the way to the ends of the time span. But we do have to tell it what the times are, which is why there's a T here. Also, I did my boxcar filter on 120 data points or 10 years. I did the same with the tent filter. What time scale should I choose for my Gaussian smooth? Well, the time scale in a Gaussian smooth is kind of like a standard deviation of a normal distribution function. Well, the width of the normal distribution is infinite because it goes to infinity, but the effective width, where you can actually get significant power, is about 4 standard deviations wide, because normally most of the data falls within 2 standard deviations above and below, so it's 4 wide. Well, that means if I want something that's roughly comparable to a 10-year wide interval, I would want a standard deviation or time scale, which was 1/4 of that, or 2.5 years. So I'm going to compute a Gaussian smooth on a 2.5-year time scale, and I have to pass it the time as well as the data values, and I'm going to give this plot equals true, so it'll give me a nice plot. Well, there it is again. It looks very similar to the others. That's not a surprise. They're all decent smoothing methods, so they should all be returning approximately the same values. I can also say that it compares very well with the true signal, which is a flat line of nothing, and that there are some moments when the 95% confidence interval does not include the true value because that's the nature of randomness. I can compare it to the boxcar filter and see that they're following roughly the same path, although the boxcar filter is kind of choppy. I can compare it to the tent filter, and once again, following the same general path. By the way, I can make a close-up of just the smooth values. Here is the Gaussian smooth with its 95% confidence range compared to the true signal values. You can see over here at the end, the confidence interval excludes the true value. That's the nature of randomness. It's going to happen. I can also compare that to the tent filter and its confidence range. You can see that the results from the Gaussian smooth and the tent filter are extremely similar. They are following the same path, which is wiggling around the true value, and they indicate roughly the same amount of probable error or uncertainty in our smoothed estimates. I can do the same thing with the boxcar filter and its confidence range. Once again, all 3 filters are following roughly the same path. They're all wiggling around. The boxcar filter is kind of choppy, but the others are more smooth. But they're all wiggling around the true value, and they all have roughly the same uncertainty level because I've done them all on about the same time scale. For the boxcar filter and tent filter, it was a number of data points scale, but it was chosen to be about a 10-year time span. For the Gaussian smooth, it was a 2.5-year time scale, but that corresponded to a roughly 10-year wide smoothing interval. So, no surprise there that we got what we expected. I'm going to demonstrate for you just briefly in this particular video another one called a low S smooth. I'm going to do a low S smooth again on a 10-year time scale. And if I plot that on the same graph, we will see that it follows pretty much the same path. I can't show the confidence interval from this computation because the built-in program, which I used from R, doesn't compute a confidence interval for you. But it would be about the same size as that from the other smooths. In the next video, we'll look at my own homegrown low S smoothing program, which does compute confidence ranges.